So, today we are going to start the second part of module 5, which is on the subject of solution of linear algebraic equations, but using advanced methods. We have seen, to briefly recap, that we have a standard scalar transport equation, and if we discretize it, we finally get a set of linear algebraic equations or linearized algebraic equations, and it is a solution of these that we seek, because the solution of these will give us the values of the variable, in this case phi, at the grid point I comma j. Okay. So, we have seen that the solution of Ax equal to b or A phi equal to b is not a trivial thing for CFD type of problems, because we would like to have, and given the computational resources at our disposal, we tend to have large number of grid points, and large number of grid point means large system of equations to be solved. So, we need to be very careful in terms of what kind of methods we choose to solve this. We made the point that the Cramer's rule cannot be used for more than 30 equations and 30 grid points, and methods, established methods for the solution of Ax equal to b, like Gaussian elimination, LU decomposition, although they are very general, they are not so good as some other methods like the iterative methods that we have also seen in the first part of this module. We saw two basic iterative methods, the Jacobi method and the Gauss-Seidel method, and we have seen that these are fairly easy to implement and write programs for, and they tend to have an arithmetic operation count which varies as n square, where n is the number of equations to be solved, compared to n cubed for Gaussian elimination or LU decomposition method. We have also seen one very good direct method, the tridiagonal algorithm, in which the operation count varies as n, but that is not applicable for the general case. It is applicable only for one dimensional problem with 3 diagonals. And so, when you look at the more generic method, then those are n cubed, whereas the basic iterative methods that we have seen vary as n square for a class of problems related to like those have happening in CFD type of problems. And we have also seen that in these iterative methods, we do not solve Ax equal to b directly, and we solve it in an indirect way, like Qxk equal to q minus a times xk minus 1 plus b, and approach the solution asymptotically. And in the Jacobi method, q is the diagonal, all the diagonal elements of A, and therefore this iteration becomes like xk equal to m xk minus 1 plus n. And similarly, in the Gauss-Seidel method, we choose q to be the lower triangular part of A, including the diagonal elements, and that again can be put in the form of xk equal to mxk minus 1 plus n. Once you have this kind of formulation of the problem, then we solve with an initial guess, which can be arbitrary in the case of convergent schemes. We start with any initial guess, and then we get x1 from, you put x1 here, you get x2 and so on, and then we keep on doing it, and eventually the solution converges for a convergent scheme. We also saw that in actual computations of Ax equal to b using the Jacobi method and Gauss-Seidel method, we do not do matrix inversion, but we rewrite them in this simple way. We reposition them in the simple way so as to get an estimated value of x1 k plus 1, x2 k plus 1, x3 k plus 1, all the way up to xn minus k plus 1 and xn k plus 1 in a sequential way, using all the guess values or the last previous iteration values of all the other variables. And we have also seen that the way that we solve the Gauss-Seidel method and Jacobi method, they are slightly different. In the Gauss-Seidel method, we make use of the updated solution of some of the variables. Wherever they become available, we make use of the updated one. Where the updated one is not available, we make use of the old solution. Okay. But and we have also seen that the number of multiplications or divisions varies as n square, and we still have to do a lot of iterations. But because we have A as a very sparse matrix, both Gauss-Seidel method and Jacobi method can take advantage of the sparseness and do this multiplication operations only on those non-zero coefficients, so that the actual number of arithmetic operations to go from step k to step k plus 1 is only of the order of phi n for a 2D and for 7n for a 3D compact molecule. Okay. But we also saw that the actual number of arithmetic operations depends on how many times we have to solve this xk plus 1 equal to mxk minus 1 plus n in order to get a solution that is fairly close to the true solution. Okay. So, and we also saw one of the characteristics that these methods do not work in all cases. We have taken this simple 3 unknowns equations problem with 3 equations, and the solution can be seen to be 1, 2, 3 for x1, x2, x3. And for this thing where we know a solution, we know the solution and we can show that the solution is unique, we find that the Jacobi method works very quickly. It gets into that within 3, 4, 5 iterations, whereas the Gauss-Seidel method diverges. So, to that extent, although these methods are simple, they do not always work, and the Gauss-Seidel method, even though it is updating, it is making use of the latest value, is not necessarily faster or better than Jacobi method. So, we need to do a proper convergence analysis, and we start with that convergence analysis in the second part of this, and we look at how we establish that there are certain conditions in which these iterative methods can be convergent, and then we look at what we call as the asymptotic rate of convergence, and we characterize an iterative method by this rate of convergence also, among other things. And then we show that there are certain methods which are better than these basic methods in terms of the convergence rate, and we discuss a few of those things. So, this is what we are going to do in part B, and we start with the convergence analysis. So, in iterative methods we have Ax equal to be solved as xk plus 1 equal to pxk plus q for k greater than or equal to 0. So, k equal to 0 is the initial guess, and from that we get x1, x2, x3 and so on. If we define error epsilon here as x double dot minus x, where x double dot is the exact solution, that double dot is just an easy way of writing it using the script language that is available. So, it does not have any, it is not like acceleration of x, it is not like d square x by dt square, it is just a symbol. Okay. It is just to distinguish between the exact solution, which is this x double dot, and the current solution, which is xk. Okay. So, the exact solution is such that when you substitute x double dot into this, you get ax equal to ax double dot equal to b, and this satisfies this equation, it also satisfies this equation. So, we also have x double dot equal to px double dot plus q. So, this is the exact solution, and if you know the exact solution and if you know the current solution x, then you can define error as the exact solution minus the current solution. So, you can say that the error at the kth iteration is the exact solution, which is always the same for a given Ax equal to b, minus xk. And we also have xk such that once you put this is the one by which we are getting xk or xk plus 1, and if you have xk, you can put that into this equation and find out what is axk, and axk need not be equal to b. Okay. So, it is equal to bk. Okay. So, the difference between bk and b is what is known as the residual, and this residual means that there is a residual amount of dissatisfaction or unsatisfaction of the given equation Ax equal to b by the current value xk. So, if you substitute xk into this equation and then you get bk, and if bk is equal to b, then xk is the exact solution because it is satisfying this equation. So, the difference between b and bk is therefore the amount of non-satisfaction of the equation Ax equal to b by our current guess or current estimated value of xk. So, this is the residual amount that still needs to be satisfied. Okay. So, how can we get that? We can put this delta k as b minus axk. Although we cannot compute error because we do not know the true solution, we can readily compute the residual, because in order to compute the residual you just have b, which is known because the problem is given, and then xk is the current estimate value. So, we know this, and a is also known. So, b minus axk is the residual. If the residual is 0, the solution has converged. Okay. If it is not 0, it has not converged and we need to do more. If the residual is very, very small, then we can say it is okay, it is pretty close to the solution. If it is satisfactory to me, then I will take it. Okay. If it is satisfactory to me in the sense that it is not, there is nothing personal here. If I see the previous iteration value and the current iteration value, and if the two differ by only in the 5th decimal place or the 8th decimal place, then maybe I say that okay, it is accurate enough for my purposes and I can stop. Okay. So, we would like to decrease the residual, and when you look at it closely, this delta k is the superscript telling us how many iterations we have done starting from the initial guess. But this delta here is not for a single equation, it is for the entire set of equations, and since we are writing delta equal to b minus bk, b and bk are both column vectors. So, delta k is also a column vector. So, that means that it indicates the amount of non-satisfaction of Ax equal to b for each equation. Okay. So, that means that when you say delta k residual is 0, that means that each value of this column vector must be 0. That means that each of the n equations of Ax equal to b must be satisfied, or they should be so small. Now, how do we say that this delta k is small? Because delta k is set of numbers. For the first equation it is 0.0015, second equation maybe 0.3025, maybe for the third equation 0.20117, something like that. So, what is small and which one of these is small? We bring in the concept of norm of this vector. Okay. So, the norm can be the largest of these n elements is one measure of the norm is a measure of the bigness of the magnitude of the elements that are there in that particular vector. Okay. So, it can be the maximum value of delta of any element of delta must be less than certain value, is one particular way of saying that every equation needs to be satisfied to within this much tolerance. Or you can say that some root mean square value of all the elements must be so much. So, that is equivalent to an L2 norm kind of thing. Okay. So, we can define those kind of norms of the vector, and in this case the vector is the residual, and then we can look for the norm of this residual vector to be smaller than a certain value. And if you say that if it is smaller than that value, then you can say I have got a solution which I feel is close enough. And typically what kind of values do we say? We would like to have a delta k which is a small fraction of the delta 0. Okay. You have x 0 to start with, and then you can put that x 0 here, and then you get b 0. So, b 0 minus b minus b 0 will give you delta 0, and we would like delta k to be reduced by orders of magnitude compared to the original value of delta, and that seems to be a good way of measuring what is small, because small is with respect to what you started out with. If you put the problem in kilometers, you will get small values 1.2, but if you express the same thing in meters, it will become 1200, and if you express the same thing in millimeters, then it will become 12 million or 1.2 million. And so in that sense, it is not the number, because the number changes with the units. We would like to make sure that the residual is changing relatively. So that is why we can say that delta not delta 0 divided by delta k should be less than, should be about greater than, say, 10 to the power 3 or 10 to the power 4. We know that delta k is decreasing as k is increasing, because it is a convergent scheme. So we are slowly approaching that. So in that sense, we would like the delta k to be at least say 1000 times smaller or 10,000 times smaller than the beginning value. So we look for orders of magnitude reduction of the residual. Okay. So how many iterations does it take to reduce the order of magnitude of the residual by a factor of 10 or a factor of e is known as asymptotic convergence rate. We will come to that shortly. Okay. So if we have this one here and we have this, if you subtract this from this, you get x double dot minus x k plus 1 is epsilon k plus 1. So the error at k plus 1 is p times x double dot minus x k. So that is error at k, this, and q will cancel out. So by subtracting this from this, you can say that error at k plus 1 is p times error at k. So in the simplest sense, if epsilons were not vectors, if p is not a matrix, okay, so then you could say p is a multiplication factor. Okay. So the error at k is being multiplied by a factor given by p, and that is the error at k plus 1. So this multiplication factor or the amplification factor is how the error is changing, and it is not constant, the multiplication factor, but it is an indication of whether the scheme is convergent and how fast it is converging. If obviously if p is less than 1, if it is a scalar, then you could say you have a convergent scheme, because if p is 0.9, next time it is only 0.9 of the current value, next time it is 0.9 times 0.9, 0.81. So in that sense it is gradually decreasing. So at the end of m iterations, you can say that the error at m, this should have been a superscript, is p raised power m times error at 0. So if p is less than 1 in magnitude, then you can say the error is decreasing at this rate, okay, at a rate which is a function of this magnitude of p. Okay. So what is this magnitude of p here? It is again not some it is not the magnitude of the it is not the norm of p or anything like that. What we are looking at is an error which is governed by its eigenvalues, okay, and so we have something called the spectral radius of the iteration matrix P, and spectral radius is the largest eigenvalue. Okay. Given that we are dealing with A which has real coefficients and no imaginary coefficients, we expect the eigenvalues of P to be real. Okay. And we say that so at the end of m iterations, the error at after m iterations, where this m should be superscript here, is equal to p raised power m times error at the first iteration. And if p is less than 1, then we can see that the error at nth step will be less than the error at this, and each time it's being reduced by a factor which is given by the magnitude of p. Now in this particular case, p is not some simple factor. The residual usually varies in a it can vary in a monotonic way like this, and in some cases it can even increase and then decrease. Okay. So here we have at kth iteration we have xk, and we can compute axk equal to bk, and then we define this residual k. And residual reduction is not uniform, it does not decrease at the same rate along with iteration number, but one can do some mathematics and say that it is governed by the eigenvalues of the iteration matrix, and these eigenvalues are going to be some are going to be large and some are going to be small. There are n number of eigenvalues for n system of equations. So if you have million grid points, you will have million eigenvalues. Okay. So all of those eigenvalues will be contributing to the reduction of error at all the time, but those eigenvalues which are small will die out first, their influence dies out first, and the largest eigenvalue is the one which is going to ultimately determine the rate at which how fast the residual is decreasing. Okay. So as you go through this iteration number, initially you have usually a steep variation because the small eigenvalue contribution is decreasing pretty fast, and eventually when you put this on a log scale and this on a log scale, okay, log scale and this is linear, you will see something like a logarithmic decrease, gradual decrease with a slope which is no longer changing. Okay. So in this part there are different eigenvalues and all of them are contributing here, and sometimes they contribute in such a way that initially the error does not decrease especially in practical CFD computations, but then it eventually starts decreasing, and as it gets closer to the solution then it will be decreasing at a constant rate, at a slope which is essentially the slope of this residual versus iteration number tells us at what rate it is decreasing. Okay. So this the constant slope at which it is decreasing for large number of iterations, for large number of m here, is known as the asymptotic rate of convergence. Okay. So that asymptotic rate of convergence is governed by the largest of the eigenvalues of the iteration matrix, and that is known as the spectral radius of the iteration matrix. So we need to know the spectral radius, we do not need to know all the eigenvalues, all the million eigenvalues, we need to know what is the largest eigenvalue. If the largest eigenvalue is less than 1, then we have a converging method, and the rate at which it converges depends on the spectral radius of this. So we will come back to this. As I mentioned, you have n by n matrix here, and if you have a million grid points, million unknowns, you will have million eigenvalues. Okay. And there is no easy way of finding all these eigenvalues, but for some class of problems it is possible to get a theoretical expression for the eigenvalue. For example, for central differencing of the Laplace scheme, Laplace equation in 2D with Dirichlet boundary conditions, we have done this. So with uniform spacing in x and y and having m by m, that is m square number of grid points. So we have in the x direction m grid points, and in the y direction we have again m grid points, so that we have a total number of m square grid points. The spectral radius of the iteration matrix with the Jacobi scheme is given by cosine pi by m. Okay. So, that is roughly equal to 1 minus pi square by 2 m square for large values of m. So, that is, if you have a few divisions, like you have a 4 by 4 matrix, then this may not be applicable, but if you have 40 by 40 or 100 by 100 for large value of divisions m here, then the largest eigenvalue is given by 1 minus pi square by 2 m square. Now, what does this mean? This means that if you are looking at m equal to 50, then this is equal to 1 minus pi square is about 10 by 2 m square, this m is also in the denominator. Okay. So, that means that 2 by 50 square, 2 by 2500, so that is the total will be 10 by 5000, so that is 1 by 1000, so this will be equal to 0.999, this whole thing will be equal to 0.001. So, 1 minus 0.001 is the largest eigenvalue. Okay. If you take m to be 100, then this is 1 minus 10 by 2 times 100 square. So, that is 2 times 10 to the power 4, 1 by 10 by 20,000. So, this eigenvalue, largest eigenvalue will be 0.9998. Okay. So, it has increased from already large value of 0.999 to even larger value of 0.9998. Now, what is the difference? The rate of convergence is determined by how far away from 1 the spectral radius is. Okay. So, in one case, in the case of m equal to 50, it is away by 0.001. In the case of m equal to 100, it is away by 0.0002. So, that means it is away by a factor of 5, and so that means that the convergence rate will be lower, will be less for larger value of m. So, as m increases, then the spectral radius approaches 1, and the closer it is to 1, the slower it is to converge. Okay. Now, for this Gauss-Seidel scheme for the same Laplace equation 2D with the same kind of number of divisions here, the spectral radius is known theoretically to be cosine square pi by m. Here it is cosine pi by m, and so that is 1 minus pi square by m square, whereas here it is 1 minus pi square by 2 m square. This 2 is this whole thing is in the denominator. And what does this mean here? If you have m equal to 50 and pi square is 10, so 10 by 250, 2500, so that is 0.996. So, instead of 0.999, it is 0.996, and for m equal to 1000, m equal to 100, this will be 0.9999 and not whatever the value that we had earlier. It is 0.999 and we had 0.9998. So, that means that the spectral radius for a Gauss-Seidel method for this problem is always less than the spectral radius for the Jacobi method. And since the spectral radius determines the asymptotic rate of convergence for large values m, from this we can say that the Gauss-Seidel method for this particular problem, where we know the spectral radius analytically, is faster than the Jacobian method. Okay, Jacobi method, and we can also show that it is faster by a factor of 2. Okay, for large values of m. And we would also like to mention that in these methods, it is not all the eigenvalues that are contributing to the rate of convergence, it is only the largest eigenvalue that is contributing to the rate of convergence. There are other methods where even these values, intermediate values of eigenvalues, will also contribute to this. Okay. So, other thing we would like to mention here is that as m increases, for the same method the spectral radius approaches is closer to the value of 1, and therefore it becomes slower and slower. Okay. So, what we would like to take from this first lesson of part 2 of this advanced methods, through some convergence analysis, we have essentially shown that for a typical iterative method, the error and the residual decrease as a function of the rate of decrease is determined by the eigenvalues of the iteration matrix, and if the iteration matrix changes, then the convergent behavior also changes. We have also seen the condition that for convergence the spectral radius of the iteration matrix should be less than 1, and the rate at which it converges under asymptotic conditions, that is for large values of m, in which the influence of the smaller eigenvalues dies out, is given by the spectral radius. The closer it is to 1, the slower it is to converge. Okay. We do not know these eigenvalues for the general case. Okay. So, in the specific case of Laplace equation, 2D Dirichlet boundary conditions, Jacobi method, uniform spacing and all that, then there are certain mathematical formulas, expressions we can derive, and these expressions show that the Jacobi method has a higher spectral radius than the Gauss-Seidel method for the same grid spacing and all that, and therefore it converges slowly, and its rate of convergence, asymptotic rate of convergence, is is half as much as the Jacobi method. Okay. So, this is the kind of error reduction that we can expect, and for large values of m, the iteration number, the residual decreases at a constant rate, and that constant rate is expressed like this. For the error to decrease by a constant factor, okay, it is not a summative factor, it is a multiplicative or divisive factor. Okay. So, it is by a constant factor, multiplicative factor, then it takes the same number of iterations. So, that is, if you are looking specifically at error reduction by a factor of 10, then it is given, the number of iterations is given by 1 by minus ln of 1 minus rho here. Okay. So, we have rho is a spectral radius. So, ln of 1 minus rho is the 1 by ln of 1 minus rho is the rate at which is the number of iterations which are required to reduce the error by a factor of e, which is 2.71 or something like that. So, if you want to reduce the error by a factor of 10, then it will take you 2.3 times log of 2.3 divided by log of 1 minus rho there, and so that fixes the number of the, if you put this on a log scale here, and then if you put the iteration number on a linear scale, then to go from say 4th decimal to 5th decimal, it takes so many number of iterations, and then from 5th decimal to 6th decimal, then it takes again the same number of iterations, and 6th decimal to 7th decimal, again it takes the same number of iterations. So, you can, in a way, you can anticipate how many more iterations you have to do in order to get convergence to within the 5th decimal or 6th decimal, 7th decimal, like that, and you can stop at some point. So, in usual conventional practice, for the usual solutions where you are not demanding huge amount of accuracy, you could say that I would like to stop my iteration once my residual decreases by a factor of 10 to the power 4 or 10 to the power 5 from the initial residual. And so, if you take that kind of thing, and given that there is a faster reduction here, and given that this is slower reduction, typically you would like to bring this down to a very low value, and this determines the total number of arithmetic operations, iteration numbers that are needed for this. And that number varies, as it is estimated to be about 0.466 n, where n is the number of equations, okay, a number of unknowns. Okay. So, it is about 0.5 n for every tenfold decrease in the residual reduction. Okay. So, if you are looking at 5 orders of magnitude of reduction, then it will take 2.5 n number of iterations in order to reduce the residual by a factor of 5 and get to our closure stoppage of the iteration. So, that means that you start with some guess value and you carry out 2.5 times n number of iterations to get to the final value in your Gauss-Seidel method or Jacobi method. So, it is something proportional to n, and each step takes about 5n or 7n number of arithmetic operations. So, the total number of arithmetic operations is the number of operations per step times the total number of steps that you want to take. So, the first step is 5n for a 2D problem, and that is the number of arithmetic operations per step, and you have to take something like 2.5 n number of steps. So, the total number of arithmetic operations is 5n times 2.5 n. So, that is about 12.5 n square. So, that means that in the Jacobi method or the Gauss-Seidel method, for this Laplace problem, you can say that it takes about 10 to 15 n square number of arithmetic operations, where n is the number of unknowns, number of grid points, and this needs to be compared with n cube by 3 number of arithmetic operations which are required for the Gaussian elimination method. Okay. So, if your n is of the order of 100, then maybe there is not that much of a difference, but if you have a million grid points, which is not unusual, then your Gaussian elimination would take million cubed. So, that is 10 to the power 18 number of arithmetic operations, and Gauss-Seidel method will take only 15 times n square. So, that is 15 times 10 to the power 12. So, this is 10 to the power 13 number of arithmetic operations. So, there is a huge difference between Gaussian elimination and Gauss-Seidel method for such kind of problems, which is why typically these Jacobi method and Gauss-Seidel method can be used for most of the problems where you have diagonal dominance, and in such case this is it takes n square number of operations, and therefore these are considered to be superior to the other to the Gaussian elimination or those type of direct methods. So, in the next lecture we will see how we can improve on this convergence rate of n square number of operations.